Good morning, my YouTube viewers. It is Crystal here, and I'm just here this morning because I wanted to give you a review of a research paper that I have found on the internet. And the research paper is entitled A Comparison Between Arima, LSTM, and GRU for Time Series Forecasting. And this paper was published for the 2019 Second International Conference on Algorithms, Computing, and Artificial Intelligence. So the work that was done is about 4 years old, but I wanted to go ahead and do a review of this research paper anyway. So the abstract is a critical area of machine learning is time series forecasting, as various forecasting problems contain a time component. A series of observations taken chronologically in time is known as a time series. In this research, however, we aim to compare 3 different machine learning models and making a time series forecast. We are going to use the Bitcoin's price dataset as our time series dataset and make predictions accordingly. The results show that the Arima model gives better results than the deep learning based regression models. Arima gives the best result at 2.76% and 302.53 for MAPE and RMSE respectively. The gated recurrent unit, however, performed better than the long short-term memory LSTM with 3.97% and 381.34 of MAPE and RMSE respectively. And that's all they give you is the abstract, and then they give you the references. So if you want to actually see the paper, you have to request it, and then you have to say where you're from and stuff like that. But I'm not sure exactly if you have to pay for it. And since I'm on like limited resources, I'm on pretty much a fixed income. I can't, just pay for things. So if it's not freely available on the internet, then it's very hard for me to acquire it. But I did get the abstract, and I decided to, in my efforts, to replicate what they did. So basically, in order to replicate what they did, I had to get a Bitcoin CSV file. So I got the Bitcoin CSV file from Yahoo, and you can download it from Yahoo if you want, which is what I did. I downloaded it. So now that you know the research paper and you know the Bitcoin CSV file that was taken off Yahoo, what we're going to do is we're going to cover the 2 programs that I have written to try to determine which algorithm works best for predicting on Bitcoin in time series forecasting. So the first thing that we had to do was we created a program, and I had an Arima program already, so I just sort of like used it. So we were going to use stats model because the Arima algorithm is in stats models. So we wanted to import the most current versions of NumPy, SciPy, Patsy, and Pandas, but I've never heard of that. And then we wanted to upgrade stats models. But the thing about Google Colab is it's got those programs already installed. And since it's got those programs already installed, you might have to install the updates, but that's about it. So the thing that you need to know about stats models is it's had quite a few revisions, and some of its code is deprecated. So you need to know which version of stats models that you're actually using. And probably what I should have done was to say, and that will print out the version of stats models that you're using. Let me just see if it did it. We got the version, and yeah. So that will print out the version that you're using in stats models. So what we wanted to do is we wanted to import our libraries that we're going to use to execute the program. So we're going to import pandas to create the data frames and process the data, NumPy to create NumPy arrays and make numerical computations, math to perform mathematical computations, sklearn to perform machine learning functionality, stats models to perform the time series, matplotlib to perform the visualization, and Seaborn to perform statistical visualizations. So they also made it to where you can ignore the warnings. So after we have imported the libraries, what we want to do is we want to read the CSV file. So we had to read the CSV file from my Google Drive because I had to download the CSV file from Yahoo, and then what I had to do was I had to read it from my Google account. So we made the index column 0 is your column, and we're going to parse the dates. So that was done automatically, and we only want to use the column 4. So series equals df.iloc, all of the rows, and then column 4. And then so here, this is what you've got. That's all we want is a univariate time series model or time series data. So the date is your index, and the adjusted close is what we're going to be predicting on. I'm going to check to see if there's any null values. There's not any null values, but just in case that there's any null values, we're going to backfill any null values just in case there were some, if there had been any null values. And now what we're going to do is we're going to plot the series. We're going to plot what the time series looks like over a course of a year, because I only got the Bitcoin data for the last year, and I think that in Yahoo, I think you can get Bitcoin data for longer, but I just got it from the last year. So that's what the Bitcoin data is for the last year. So you can see that it's increasing. It was decreasing, now it's increasing. So we're going to create a histogram of the values, and you can see there's a histogram of the values if you want to see it. And now what we're going to do is we're going to create a two-sided view. So if you like two-sided views, you can look at the two-sided view as well. We're going to do some statistics. So it says, but I didn't use these, so it doesn't matter. I didn't use these, that's probably why. I didn't. I just skipped right through it. But you can see that you get the maximum value and the minimum value. So the maximum value was 364 and the minimum value was 130. Now what we're going to do is check for stationarity. And so if we look for a p-value. If the p-value is less than 0.05, the time series data can be said to have stationarity. So the p-value is greater than 0.05, so it doesn't have stationarity. But I used it anyway, and the reason why is because in order to review this paper, I had to make the circumstances as close to what the original researchers did as possible, and since they used a CSV from Bitcoin, I'm using a CSV from Bitcoin. So now we split the data frame up into training and testing frames, and you can see that the trained data frame has 329 rows, whereas the test data frame has 37 rows. And I was doing lots of experimentation on this program, so I designed the variables train IDX equals train index and test IDX equals test index. And the reason why is because I couldn't get it to work, and I was trying all of these different methods to try to get the program to work. Now we're going to scale the data. We're going to use sklearn's min-max scaler, and we scaled the data because the data and the other program was scaled. So I wanted to keep the scaling. If the scaling was done on one program, then I needed to do scaling on another program. So I wanted to keep the factors the same. All of the factors within the program's the same. So we had scalar equals min-max scalar dot fit train, series dot scale equals scalar dot transform series, because I was trying all different kinds of things to try to get the program to work. So I decided to transform series as well. Train scaled equals scalar dot transform train. Test scaled equals scalar dot transform test. So we did another stationarity test. So you're just checking the difference between the train test and the test set. But I didn't really use it because I knew that I was going to be using the Bitcoin CSV file. I had to use it. But you can see that you can check the mean and you can check the variance. So now what we're going to do is we're going to analyze the test set. So these are the values of the test set. We're going to do a seasonal decompose, but I didn't really use that in this program, but I kept it in there. And now we get to the Arima, and that's what we're going to be using is the Arima model. So your Arima has three components. So AR is the auto aggression, P is the order of AR, MA is the moving average, Q is the order of MA, and integrated is differencing, D is the order of I. So we set it up as P values equals range 0 to 8, Q values equals range 0 to 8, D values equals range 0 to 3. And so now what we're going to do is we're going to evaluate the combinations of PDQ and the Arima model. And so we've got the code there to do that. And then so when we did it, we found out that the best PDQ value was 425. So what we did was we imported the Arima model from stats models. So model equals Arima, train scaled equals order 425 fit, model AIC, and then so you see that the AIC is the negative value. So now what we're going to do is we're going to make predictions and then also plot those predictions on a graph. So we're going to transform the data back to the original data space. So test equals scalar dot inverse transform test scaled. Train equals scalar dot inverse transform train scaled. And then we're going to make the prediction. So y hat equals model dot prediction, not model dot predict. Start equals len train, n equals len series minus 1, dynamic equals false, y hat equals scalar dot inverse transform y hat dot shape -1, -1. And now we're going to plot the data. So you can see that we plotted the data, and we did actually use train index IDX. So we say that the plot the figure is 10.4, plt.plot train IDX, train label equals x train, plot label test IDX, test label equals x test, plot plt.plot test IDX, y hat label equals Arima forecast, plt.legend best, plt.title Arima forecast, plt.show. So we plotted it and it worked. And I did spend quite a bit of time trying to get it to work, and so that's why I had to define the variables train IDX and test IDX. So now we calculate the MAE, that's your mean absolute error, and your RMSE. So they give you calculations for mean absolute error and RMSE. So now you can see this is your Arima forecast. So you can see the X train, the X test, and the Arima forecast. So the Arima forecast is almost just a straight line. And your RMSE is 3026 or almost 3027. And then what we do is we create data sets out of train and y hat, and we check our RMSE again. And the value between the RMSE here is different. The value is 91 RMSE, but the value that we got here is 3026. But we're going to go ahead and use the 3026, and the reason why is because that is the programming, the code that we're going to be using in the next program. And since that's the code we're using in the next program, we want to keep everything the same. And then so we're just going to go ahead and stick with the RMSE of 3027. And then the other RMSE of 91, we're not really going to worry about that so much in this instance, because what we want is we want everything as much as possible to be the same between the two programs. And then we created a data frame so you can see the values of the actual values and the predicted values. So you can see that as far as the Arima is concerned, it tries to stick with the value of the last point taken before it starts making forecasts. So that's it. So this is your Arima. So you can get a good look at the Arima. Now what we're going to be using is we're going to be using Bitcoin, LSTM, by LSTM, and GRU. But we're only going to be, for this purpose, we're only going to be using LSTM and GRU. And the reason why is because that's what the researchers did. So LSTM stands for long short-term memory, and GRU stands for gated recurrent unit. And you can see here we had to create another program because that was we were using TensorFlow. So we're going to import pandas as PD to create the data frame and process the data. We're going to import NumPy as NP, and what that is going to do is to create NumPy arrays and perform numerical computations. We're going to import sklearn to give you machine learning functionality. We're going to import matplotlib to visualize the data. We're going to import Seaborn to statistically visualize the data. And we're going to import TensorFlow to provide neural networks. We're going to set the random seed, so every time you run the program, it'll be the same. We're going to read the file in the same manner that we read the file in the last program for the Arima, because we want to keep as much the same as possible. We're going to check for null values. There's not any null values, but just in case there were any null values, we were going to backfill them. So we're going to visualize the data just like we did in the last program, so you can see how the data has been visualized. We're going to split the data into training and validating sets. So it's very similar. We did it very similar to the way that we did it in the last program, but instead of calling it train, we're going to call it train data. Instead of calling it test, we're going to call it test data. We're going to scale the data. We're going to use sklearn's min-max scaler. And so therefore your data is trained. So you're going to have train scaled and test scaled. And now we're going to create the data set. So the input shape should be samples times steps features. So def create data set, x look back equals 1, xs yx is 2 blank list or arrays. For I in range, len x minus look back. V equals x I colon I plus look back. Vs append xs dot append v, ys dot append x I plus look back. Return NP array xs and then NP array ys. So now you've got your x and your y variables. And so x train, y train equals create data set, x train scaled 1. And x test, y test equals create data set, test scaled 1. And then we print the shapes of x train, y train, x test, y test. So you can see x train is 328, 1, 1. Y train is 328, 1. X test is 36, 1, 1. And x test is 36, 1. And now what we're going to do is we're going to create the model. So really, we created 3 models, but we're only going to talk about 2. We're just going to talk about the GRU and the LSTM. We're not going to talk about by LSTM. We will do that in another program, another video, another blog post. So we create the GSU. This model equals sequential. Input layer equals model.add GRU. Units equals units. Return sequences equals true. Input shape equals xtrain.shape1, xtrain.shape2. Model.add dropout 0.2. Hidden layer model.add GRU. Units equals units. Model.add dropout 0.2. Model.add dense units equals 1. Then we compile it. Model compile optimizer is Atom, loss is MSE, and you return the model. And then so we create the model with model GRU equals create GRU is 64. Now we're going to create the LSTM. So def create LSTM units, model equals sequential, and then we're going to create the input layer, model.add LSTM units equals units, return sequences equals true, input shape equals xtrain.shape1, xtrain.shape2. We create the hidden layer of model.add LSTM units equals units, model.add dense. So that's your output layer. And then we're going to compile the model, model.compile, optimizer equals atom, loss equals MSE, and then you return the model. And we're not going to worry about by LSTM because the people that made the program, people that made the research paper didn't use by LSTM, so we're not going to worry about that. Now we're going to, and then we also created the model. So saying model LSTM equals create LSTM 64. Now what we're going to do is we're going to fit the model. So def fit model, model early stop equals caris dot callbacks dot early stopping monitor equals valve loss, patience equals 10, then history equals model dot fit, x train, y train, epochs equals 100, validation split equals 0.1, batch size equals 16, shuffle equals false, callbacks equals early stop. And then you return the history. And then so we fit the GRU and the LSTM. And then so this all runs, all the epochs runs. Now what we're going to do is we're going to check model performance. So we check the GRU history, and you can see that the valve loss was very low. You can see that on the graph. We check LSTM. Again, you can see here that the valve loss is also very low. We won't worry about the by LSTM. So now we're going to make predictions on our data. So y-test equals scalar dot inverse transform y-test. Y-train equals scalar dot inverse transform y-train. And we're going to make the prediction. So def prediction model, prediction equals model dot predict x test, prediction equals scalar dot inverse transform prediction, and then you return prediction. So we're going to have the predictions for the GRU and the predictions for the LSTM, and then we're going to plot it. Plot test data versus prediction data. So you can see that we have plotted it. So plt.figure, figure size equals 10.6, range equals len prediction, plt.plot, np arrange, range future, np arrange, y test, label, x test. plt.plot, np.arrange, range future, np.array prediction, label prediction. So plt.title, test data versus prediction data for model name. PLT legend lock upper left. PLT.x label is year, and PLT.y label will say that's price. And then what we do is we plot it. We're also going to calculate the MAE and the RMSE, which is the same code that we used in the previous program. So now you can see this. You can see that for the GRU, the RMSE was 575, and for the LSTM, you can see the RMSE was 728. So the GRU outperformed both the LSTM and the Arima model. So you can see what it looks like on the GRU. And you can see what it looks like on the LSTM. Very similar. But I decided I wanted to do some more visualizations with another program, some more code. I wanted to do some more visualizations. So we're going to visualize the entire code. So year new equals np.arrange 0 to len df. Year pred equals np.arrange 330 to len df. Y equals np array df. plt.plot year new y. plt.plot year pred prediction GRU REFL. So you can see when you look at what the prediction is as compared to the entire time series, you can see that the prediction is very close. And this is a picture of the LSTM. You can see that prediction is very close as well, with the exception that it didn't perform as well as the GRU. And so that's the only thing that we're going to worry about. We're not going to worry about the by LSTM. We will worry about that in another program, another video. So that's it. So you can see that from obviously I couldn't get the report, but I simulated what the authors of this report did. And the simulation that I performed, the GRU outperformed both the LSTM and the Arima. So, although I'm not sure exactly what they did, but I tried to do both of the programs as close to each other as I possibly could, which meant that both of the programs, I standardized the data because I researched this and they said that you're supposed to standardize it or normalize it. So I researched it. And since they say that you're supposed to standardize the data, then I went ahead and standardized the data both for the Arima and the LSTM and the GRU. And I did everything as close as possible that I could possibly get. And then I found that the GRU performed the best. So that's it for this review of this research paper. I hope you got a lot out of it. I hope you learned a little bit about time series forecasting. I'm going to go ahead and conclude this video, but thank you so much for watching my video. Thank you to my subscribers for supporting my channel. If you like this channel, please like, subscribe, and share. And if you want to be notified whenever I make a new video, then please tap onto the bell button next to the subscribe button.